Chapter 21: Electric Current and Direct Current Circuits. Here is the overview of Chapter 21. We will first talk about electric current and the resistance to electric current. We will then talk about energy and power in electric circuits. We'll then move on to resistors in series and parallel. We'll talk about Kirchhoff's laws and how they can be useful. We'll then move on to circuits containing capacitors, and our final topic will be RC circuits, which are circuits that contain capacitors and their resistors. Electric current is quite simply the flow of electric charge from one place to another. It is defined as follows. We represent it with the letter I, and it's the amount of charge, which is represented by delta Q, that flows through a particular point, divided by delta T, which is the time that that charge flows through that point. The SI unit is coulombs per second, which we usually use the abbreviation of ampere for. An electric circuit is a closed path which the charge can flow where it will return to its original point. A flashlight is an example of an electric current that flows through a closed electric circuit. The flashlight contains a battery which has a potential difference, and this potential difference gives rise to an electric field. The electric field, when the flashlight is switched on, will push electrons through the circuit. The electrons will go through the bulb and the bulb will light as a result, and then they will return to the battery. In order to get a potential difference within the battery, one needs chemical reactions which essentially separate the charge, so you have a buildup of positive charge on one plate and a buildup of negative charge on the other plate, and this gives us our potential difference. An analogy can be seen on the bottom where somebody is lifting water from a tray. The water flows down a surface and it pushes a wheel as a result. The water, when it pushes the wheel, returns to the tray, and then the process repeats for the wheel to continue to turn. A battery that is disconnected from any circuit will have this electric potential difference that we talked about in the previous slide. This is often referred to as an electromotive force. We represent it by the letter E. But despite its name, it really is an electric potential. The role of the force comes in because it can be used to move charge around a circuit. The amount of work it takes to move charge, which we can represent by delta Q, will be equal to delta Q times the EMF. We define the direction of current flow to start from the positive terminal and then to go to the negative terminal. This is shown by the green arrow, where one can see it flows round in a clockwise direction. This definition was decided before it was realized that electrons were really the thing that was carrying charge in an electric circuit, and these were negatively charged. So in reality, even though we define the direction of current flow to go from the positive to the negative terminal, what actually happens is electrons leave the negative terminal and they will flow in a counterclockwise direction and finish at the positive terminal. The actual motion of electrons along a wire is quite slow. They indeed spend most of their time bouncing around randomly within the wire, and they have a small velocity component, which in this case will be to the right of the diagram that we see. That small velocity component to the right is in the opposite direction to where we define the current to flow, as we discussed in the previous slide. Even though the electrons move slowly themselves, the electric signal will propagate much more quickly. The process that we discussed in the previous slide leads to the fact that a wire itself will present resistance to the motion of electrons. Without the wire being there, the electrons would move seamlessly from one end to the other. Ohm's law is something that helps us relate the resistance to the potential difference into the circuit to the amount of current that's flowing, and it's shown by the equation on the slide. V is the potential difference, I is the current flow, and R is the resistance. It's clear from this equation that when R is big, I, which is the current flow, will be small for a fixed potential difference. Now, this relation is not universal. It only actually applies to most metallic conductors. Other materials don't have this linear relation between voltage and current that Ohm's law states. Now, if we solve for resistance in the Ohm's law equation, we find that R is equal to the potential difference, V, divided by the current, I. This means that the units of resistance are volts per ampere, which we often write as ohms, and 1 ohm is equal to 1 volt per ampere. Two wires of the same length and diameter will have different resistances if they are made of different materials. This property in which they differ by is called the resistivity, and it is denoted by the symbol ρ, and one can calculate the resistance from the resistivity by taking the resistivity, timesing it by the length of the wire, and dividing it by the cross-section area of the wire. Here we have a table on the slide which shows the resistivities for different materials. Insulators, by definition, have high resistivities, which means they do not like current to flow through them. One example is glass, another one is quartz. Semiconductors are more willing to let current flow through them, so they have smaller resistivities. And then finally, we have conductors which like current to flow through them, and they have the smallest resistivities. An example would be copper or gold. In general, the resistivity of materials will go up as the temperature goes up due to thermal effects. This property is actually utilized in electric thermometers. These have a metal probe where a current flows through, and the amount of current that flows through this probe is controlled by the temperature. So if one can measure the current, one can assess the temperature of the environment the probe sits in. The opposite is true. The resistivity will usually decrease as the temperature decreases, and there are a special class of materials called superconductors where at a particular temperature, which we call the critical temperature Tc, we find that the resistivity suddenly drops to zero, and these materials have a zero resistance as a result. Here are two examples of superconductors in action. The first is the ATLAS experiment at the Large Hadron Collider, the LHC, at the CERN laboratory in Switzerland. The ATLAS experiment requires a very, very large magnetic field to operate. Electric currents can generate magnetic fields, as we will see in the next chapter. So in order to generate a very large magnetic field, one needs a very large electric current, and this is something a superconductor can provide since it has zero resistance to current. Another example is an MRI machine, which also requires a very, very large magnetic field, which comes from a large electric current, which again a superconductor can provide. When a charge moves across a potential difference, its potential energy changes. In order to change potential energy, you need to supply a power. That power is equal to delta U divided by delta T, which from the above equation we can see is equal to delta Q times V divided by delta T. Since current is delta Q over delta T, we can then show that the electrical power is equal to the current I times V, which is the voltage. For materials in which we can apply Ohm's law, we can actually express the power in terms of the resistance in the circuit. If we take our original relation, the power is equal to the current times the voltage, we can then substitute voltage with the current times the resistance from Ohm's law. This gives us a power that's equal to the current squared times the resistance. We can also do the same for the current in P equals IV. We can substitute this for the voltage over the resistance, and this gives us a power that's equal to the voltage squared over the resistance. The power in electric circuits mostly dissipates as heat when one has something that provides resistance. When the electric company sends you a bill, your usage is quoted in kilowatt hours. What they are actually doing is they are charging you for the amount of energy use, and the measure of energy is the kilowatt hour. We can see where this comes from when we look at the equation for power, which is equal to energy use divided by the time in which the energy is used over. If we rearrange this equation, we can show that the energy use is equal to the power, which a kilowatt is a measure of, times the time, which an hour is a measure of. Converting kilowatt hours into joules, we use the following relation, and we get that 1 kilowatt hour is the same as 3.6 by 10 to the 6 joules. Moving on to resistors in series and parallel. When we have a number of resistors that are connected end to end, these are said to be in series. In such a system, the same current will pass through the first resistor, the second resistor, and the third resistor in the circuit diagram shown on the bottom left. We can think of these three resistors as one resistor that has an equivalent resistance where the current I flows through that in the circuit on the bottom right. The equivalent resistance for resistors in series is quite straightforward to calculate. It is simply the sum of all the individual resistances, and it will have a unit of ohms since an individual resistance also has a unit of ohms. This is something that can be proved, and it is proved by assuming the current through each resistor is the same. An example of three resistors in parallel is shown on the right. Each of these resistors will have the same potential difference across them, but they will have a different current that flows through them, and that current will depend on what the resistance for a given resistor is. We can also think of these three resistors as one resistor with an equivalent resistance, and this is shown on the bottom right. To calculate the equivalent resistance for resistors in parallel, the inverse of the equivalent resistance is equal to the sum of the inverse of the individual resistances. This relation can be proved by assuming the potential difference across each of the resistors in parallel is the same. If the circuit is more complex, which is shown below, where one has a combination of resistors in parallel and series, one has to start with a combination of resistors that are either purely in parallel or series. The example that we show has two resistors purely in parallel. One then replaces this with an equivalent resistance and then repeats this step where we find there are three resistors in series, which we can then replace with one final equivalent resistance. Moving on to Kirchhoff's rules. There are even more complex circuits that can't simply be broken down into series and parallel pieces. For these circuits, where we see an example at the bottom of the slide, we need Kirchhoff's rules. There are two rules, the junction rule, which is a consequence of charge conservation, and the loop rule, which is a consequence of energy conservation. As we'll see, Kirchhoff's rules are very useful to help us determine a particular current that will flow through a particular resistor. The junction rule. This states that at any junction, the current entering the junction has to equal the current leaving the junction. And this is simply a consequence of charge conservation. The amount of charge that goes in has to equal the amount of charge that goes out. We have an example in this circuit on the bottom right where current I1 goes into point A, and then this splits off into I2 and I3. I1 will therefore equal I2 plus I3, which you can rearrange to say I1 minus I2 minus I3 has to equal 0. The loop rule, which is a consequence of energy conservation, states that the algebraic sum of the potential differences across the closed loop must be 0. A closed loop is defined as a loop where current can start off at a particular place and it can then return to the same place. We usually represent this by saying that the EMF, where potential can be gained or lost, plus the potential lost when a current travels over a resistor or many resistors, is equal to 0. The strategy for using Kirchhoff's rules involves 3 steps. The first step is to identify the variables for which you would like to solve for, and these are usually the currents that flow through the resistors. You will then need to set up as many independent equations as you can, and these will contain the variables you have to solve for. This is step number 2, and with step number 2 you have to use step number 3, which is to determine whether you need a loop or junction rule for your independent equation. Moving on to circuits containing capacitors. Capacitors can also be connected in series or parallel. Here we have an example of 3 capacitors that are connected in parallel. Each capacitor will have a different charge, which can be Q1 for capacitor 1, Q2 for capacitor 2, or Q3 for capacitor 3. When the capacitors are connected in parallel, just as for resistors, the potential difference across each of the capacitors will be the same, and as stated before, the charge can be different. Just as for resistors in parallel, we can think of these capacitors in parallel as one capacitor with an equivalent capacitance and an equivalent charge that is on this capacitor. For capacitors in parallel, the equivalent capacitance is straightforward to calculate. It is simply the sum of the individual capacitances, which is shown by the equation below. It has a unit of farad, since the unit of an individual capacitance is also in farad. Moving on to capacitors connected in series. Now, these do not have the same potential difference across each of them. There will be different potential differences for different capacitors. We have a diagram on the right where we have 3 capacitors, C1, C2, and C3. What they do have in common is the same charge, so the positive charge on one of the plates of C1 will equal the negative charge of the other plate in terms of the magnitude, and this positive charge on C1 will be exactly the same positive charge on C2. The total potential difference is the sum across the potential differences across each of the capacitors, and when one uses that relation, one can determine an equivalent capacitance, which will have the same charge as each of the individual capacitors. The inverse of the equivalent capacitance for capacitors in series is simply the sum of the inverses of the individual capacitances. Therefore, capacitors have the opposite relation to resistors, in the sense that for resistors in series, one uses a normal sum, but for capacitors in series, one will use an inverse sum, and vice versa for capacitors and resistors in parallel. Moving on to the final topic, which is RC circuits. If we have a circuit with a battery and a capacitor, the battery will distribute its charge to the capacitor plates instantaneously when that circuit is connected. If we then add a resistor to such a circuit, which has an open switch, we then close the switch. Charge will build on the capacitor when we close the switch, but it will take time to do so. This is known as a RC circuit. it can be shown that the charge on the capacitor will increase with time as follows. This charge, which is a function of time, will equal the capacitance times the EMF times open bracket 1 minus e to the power of minus the time divided by the time constant. Here, tau, which is the time constant, is given by the resistance times the capacitance, and the capacitance times the EMF is the final charge that will be on the capacitor after a very long time. Here we show the charge as a function of time on a capacitor in an RC circuit. Time is shown in terms of tau on this graph on the x-axis, and the charge on the capacitor is shown in terms of the total charge, which is the capacitance times the EMF. At small times, the rate of charge, which is the amount of extra charge on the capacitor per unit of time, is rather large, and as time goes on, this rate will decrease until it becomes zero at a very long time, where the charge on the capacitor will eventually be the capacitance times the EMF, which is shown by this dashed line. The current in the circuit, as the capacitor is charging, has an opposite relation. Its dependence on time is equal to the EMF over the resistance times e to the power of minus the time divided by the time constant. At small times, it will start off at the largest possible value, which is the EMF divided by the resistance, and then decrease as time goes on. It will eventually hit zero, and it hits zero when the capacitor becomes fully charged.